Hello, this is Erick with GoEngineer Tech Support. In this video, I want to talk about the importance of setting up your material in a nonlinear study and what the differences are between the static solver and the non-static solver when running a simulation study. The major difference between the linear static solver and the nonlinear solver is the linear static solver is only equipped to be able to handle stresses prior to the yield point, while the nonlinear solver has multiple options on setting out the material properties past the yield point. This region is called the plastic region of the material. In this video, we're going to talk about the Plasticity Von Mises model type and the different options that we have. What we're going to do is compare the results between a linear static study, a nonlinear isotropic model set up to resemble the linear static study, an option called the tangent modulus when you do not have a full stress strain curve available, and a full stress strain curve material in the study positive curve. Let's go over how these are set up and the slight but very important differences. If we look at the linear static study and then look at the material here, you'll see that we only have two options for the material model type. Note that we're using the tangent modulus material right here. If I select the model type, I only have isotropic and orthotropic. Those are the only options I get in the linear solver. If I look at this nonlinear isotropic model study, and we check the material property, we're also using the same tangent modulus material, but in the model type dropdown, we have quite a few other options. This study is said to be a linear elastic isotropic, meaning past the yield point, the solver is going to assume that the material properties are going to be collinear to the initial linear elastic part of the material curve. Essentially, this nonlinear study is the same as the linear static. If we look at the stresses of linear static, we have 73 megapascals. If we look at the results from the nonlinear isotropic model, we have 75 megapascals. They're very close. Now, when you don't have access to the full stress strain curve for a material, you can utilize what is called the tangent modulus. If we look at the tangent modulus study, and we look at the material property, when we're set to Plasticity Von Mises, we have the option to input this tangent modulus. What this value does is it allows the solver to assume the material properties past the yield point are driven by a line that starts at the yield point that follows a slope of the tangent modulus. This is usually 10% of the elastic modulus for testing purposes. So if we look at the results here, we have 36 megapascals, significantly lower than the isotropic model. If we look at the nonlinear positive curve study and then check the material properties, what we have done here is set it to Plasticity Von Mises. We do have a tangent modulus, but we have actually added a stress strain curve. When you add a stress strain curve, the SOLIDWORKS solver will ignore the tangent modulus even if it exists. Now, when you input your data points, the first point should be the first data point past the yield point. The nonlinear solver will create a tangent line to every one of these points, and if it finds that that tangent line has a slope of 0 or negative, it'll give you this warning. This is not an error message. This is just a warning telling you that your data points are giving you a slope of 0 or negative in case you want to review your information. If we look at the stress results here, we get 51 megapascals. It is higher than tangent modulus and lower than the isotropic or linear static study. Now let's compare these results. The linear static study gives us a high stress because past the yield point, as previously mentioned, the material properties are assumed to follow a collinear line to the elastic region of the material. This is telling the solver that this material is a lot stiffer than it actually is. If we look at the isotropic model, the nonlinear isotropic model, we have set up these material properties to actually resemble the linear static. Past the yield point, we are seeing a collinear line that matches the linear elastic region. That's why these two results are very similar. If we look at the tangent modulus model, since the material properties are set to be approximated with a straight line driven by a slope of the tangent modulus, these results are going to be a lot more conservative than having an actual stress strain curve. And finally, with the nonlinear positive curve study, where we actually inputted a stress strain curve, we see that the stresses are 51 megapascals. These are going to be the most accurate stresses. Now, to achieve a much more accurate stress, here you might want to consider using the true stress of the material or the engineering stress. All you have to do now is increase the mesh until the stresses don't change significantly. This has been Eric with GoEngineer Tech Support. Thanks for watching.